Okay, now in class we are going to handle a part called use of calculus. So here I'm going to still use the equations of motions. If this was, if the equation of motions we saw, we are using so much of the equations when acceleration is uniform and linear. So these were the ones we are using. But now, if we have variable acceleration or displacement, it means that it changes after a certain time t. So there, if that's the case, then we are going to use the differential calculus of integration. The calculus of integration and differentiation. So this topic is all about differentiation and integration. So I covered all those topics in paper 1 of integration and differentiation. You can go in the playlists or visit the channel and then check through integration and differentiation and see how we differentiate and how we integrate. Okay, so from there now, we need this integration and differentiation under this topic. So it means you go and cover them first, and then you have the idea of differentiating and some trigonometry. Okay, for a uniformly accelerated motion, the following equations are used. So these are the equations. This is the first equation of motion, the second, and then the third. Where this is the velocity, even use also velocity, S is displacement, and A is acceleration. Of course, T is the time. However, when acceleration is variable, differentiation and integration are employed. Velocity, remember, now you say velocity is the rate of change of displacement. So this is the change of displacement. So rate means that respect to time. So meaning, this means that to get velocity, we differentiate displacement, as you can see there. So here in our integration, we saw that we can separate variables. So when I separate and get this side, I'll be having now the S equaling to V dt. And we integrate this side and that, we have this and this. I get this, then when I integrate this, I leave it the way it is. So what does it mean? It means that now here, we shall substitute a function of velocity in terms of t and we integrate that. Of course, we shall be having constants of integration if we don't have limits or if our functions are indefinite. Integrals are indefinite. Okay. Acceleration is the rate of change of velocity. So it means that whenever I differentiate velocity respect to t, that's what we get. When you separate and I take this side and I differentiate this, so here I'm differentiating v, here I'm differentiating t. So if you integrate both sides, this is what we'll be getting. When you integrate and differentiate this, you are doing nothing in this function. Then it shall be having that. So that means that to get velocity, we integrate acceleration. To get acceleration, we differentiate because we said one is the reverse of the other. So if when you are getting acceleration, you differentiate velocity. It means that to get velocity, you integrate acceleration as you see. The same case here. If you want velocity, you differentiate displacement. But if you want displacement, you integrate velocity. As simple as that. Average velocity of a particle moving through or along a curved path. This is the same. Here I have this. But remember we had our V. From here we had our V as this. So where is V, I put what V is. We differentiate displacement respect to t. So it's that when this and this will be the second derivative of this, which will be represented as that. So this one means differentiation, and I'm differentiating this function twice. Okay, if a particle passes through, let us go to average velocity of a particle moving along a curved path. If a particle passes through a point with a position vector, remember this is the position vector, we said for position vector we have rt. Now at t1, we have t1, and through another point, rt2 at time t2, then the average velocity is given by this. Average velocity is equal to the change in displacement over the change in time. So here displacement can be given as r or as t. So when they use or as s. So if you see r, it means displacement, and when you see s, it means the same. Okay, so change in the displacement, we get this at time t, then minus at time t1, then over the change in time t2 minus t1. So this is how we get the average velocity. We get a difference between the displacement at the given times and over the difference in those times. Then average acceleration, if a particle has a velocity v_t1 at time t1 and v_t2 at time t2, then average acceleration between the time intervals t1 and t2 is given by change in velocity over change in time. So we get v_t2 minus v_t1 over t2 minus t1. As simple as that. So whenever you have, remember this one is like we are getting a change in the velocity over time. I think we can let them with this dv dt, d delta v delta t, change in velocity over change in time. For motions in ij plane, then if rs is equal to x plus xi plus yj, then we can write it as a column vector in this form. One velocity we say we differentiate displacement. So we differentiate the x component and then the y component. If you want acceleration, we differentiate displacement to time. So we can differentiate the x component and we can differentiate the y component twice. If we have them in the ijk plane, it's the same case. Our displacement will be this. To get velocity, differentiate these three components once. Then to get acceleration, we can differentiate them twice. Of course, if you want now, if they give you acceleration and they want you to get, if they give maybe velocity and they want you to get this, we have seen that to get displacement, you do the reverse. You just integrate. So, the next lesson now we are going to be seeing some examples about this. See you there.